Hi everyone. Today I'll be talking about air pollution. Air pollution is a concern throughout the world. If you are from Southern California, you're probably familiar with smog. Looking at different parking structures, there's actually signs that are posted throughout that give you warnings about breathing the air inside the parking structures. When we're talking about different types of air pollutions, we want to figure out first where it is from. So there's something called a point source and a non-point source. A point source, these are specific spots where large quantities of pollutants are discharged. And examples would be power plants and factories. So if we're looking at the two pictures on the bottom, the one on the left would be an example of a point source because you can point to it. You could say, aha, there is pollution that is being emitted out of those factories. If we're looking at the picture on the right looks kind of hazy. That's an example of a non-point source, where it's more diffuse. It consists of many small sources, such as automobiles. So with non-point sources, it could be moving around. You just can't pinpoint the exact location, and this can be over a large area. After we have identified the source of pollution, whether it be point source or non-point source, we can then classify pollution even further to be called a primary or a secondary pollutant. A primary pollutant is what you make first. A secondary pollutant is what you make second. So a primary pollutant says it's directly harmful. It can react further to form harmful substances, so it can form the secondary pollutants. The chemical by itself, it's detrimental for us or for the environment. And examples are soot, carbon dioxide, nitrogen dioxide, and sulfur dioxide. With soot, you've seen soot in the alternative fuels lab. I would say with the burning of kerosene. Kerosene, you could see that black soot, that black smoke that is emitted. And then carbon dioxide is a direct product of a combustion reaction. Nitrogen dioxide, sulfur dioxide, we will talk about in more detail in further slides. Secondary pollutants, this is when you have your primary pollutants, they react, they have some type of chemical reaction with some other chemical in the atmosphere, and that can form these secondary pollutants. And usually what ends up happening is the primary pollutants either will react with light or with water or with air to form that secondary pollutant. And examples of these would be tropospheric ozone, O3, sulfuric acid, there's also nitric acid, and as an example for NO2, so NO2, that was a primary pollutant, that's usually from the combustion of engines. So NO2, it's going to react with light, and then it's going to cause oxygen to create ozone, which we will talk more about in detail in another slide. Now, within the primary and secondary pollutants, there's something called criteria pollutants or criteria air pollutants. These are pollutants that are judged by the EPA, the Environmental Protection Agency, that poses the greatest threats to human health. And eventually we'll talk about legislation that was enacted to minimize the amount of these sources of pollutants. And the first one to know is carbon monoxide. There's sulfur dioxide, SO2, nitrogen oxides, NOx, so that X is any type of variable. It could be a 1, it could be a 2. There's ozone, O3, particulate matter. It's not necessarily a chemical compound. It's just in general a classification, abbreviated as capital P, capital M, and then lead, so the chemical element lead. On the right here, you will also notice it says VOC. So VOCs, that stands for volatile organic compounds. It's another type of pollutant, but it's not necessarily what we call the criteria air pollutants that are determined by the EPA. One gas you are probably familiar with is carbon monoxide. So this is one of the criteria air pollutants. It's a colorless, odorless gas. It's produced primarily by the incomplete combustion of fuel. So these are usually from hydrocarbons. If you have gasoline, if you have propane, if you have butane, if you have methane, like a gas burning stove. And if you have incomplete combustion, normally, if you have complete combustion, you're producing carbon dioxide and water. But if there's incomplete combustion, in addition to forming carbon dioxide and water, you can also produce carbon monoxide. And this carbon monoxide, it poses risks to human and animals, even in small concentrations, which is why at home, you should have a carbon monoxide detector in addition to your smoke alarm, because you can't see it, you can't smell it, you can't hear it, but it can be stopped if you have a detector. Sulfur oxides and nitrogen oxides, these are other examples of the criteria air pollutants. We'll start with sulfur dioxide. So sulfur dioxide, SO2, is a colorless gas with a strong odor. So think rotten egg smell because of the sulfur. This is produced from coal emissions when you are creating electricity and in factories. This contributes to industrial smog. Industrial smog we talked about before is that gray haze over cities. And acid precipitation. So acid precipitation, that's a fancy word for acid rain. And that's because the sulfur dioxide will react with water to make sulfuric acid. It also will reduce plant productivity and can cause breathing difficulties. With nitrogen dioxide, NO2, it's highly reactive. It's a foul-smelling reddish-brown gas. And we get nitrogen dioxide from forest fires, volcanoes, lightning, and bacterial action in the soil. With these nitrogen oxides, so there's a subscript of X just because it could be 1, it could be a 2. Nitrogen and oxygen, they react at high temperatures that will end up creating O3. It will end up creating ozone, which is a secondary pollutant. And these nitrogen oxides, they are from vehicle engine and industrial combustion, so gasoline and that combustion reaction, and from electrical utilities. These nitrogen oxides, they contribute to photochemical smog. So photochemical smog, think about the LA skyline. It's not really a gray haze. It's usually, I guess if you look at pictures, it's going to be like a brownish haze. And that's from the nitrogen dioxide. And then also will contribute to acid rain, acid precipitation. And that's because the nitrogen oxides will react with water to make nitric acid. Another criteria air pollutant is tropospheric ozone. So tropospheric ozone is the ozone that we're breathing in our atmosphere, as opposed to stratospheric ozone, which is up high, far, far away, which protects us from UV radiation. And the picture on the top right-hand corner, that is just the Lewis dot structure of ozone, in case you were curious, with the resonance structure. So ozone is a colorless gas. It has a strong odor. It's a secondary pollutant because it is formed after either the reaction with sunlight, heat, or the nitrogen oxides or volatile carbons. It is a major component of smog. So if you do get a smog check in LA, you're going to see a list of a whole bunch of chemicals, and ozone is one of them. It does pose a health risk because it causes lung irritation and damage, bronchial constriction, coughing, wheezing, and eye irritation. So this is especially irritating for people that have asthma. The last two criteria are pollutants are particulate matter and lead. Let's start with particulate matter. It is abbreviated as capital P, capital M. You are probably familiar with PM due to this pandemic this year. It's a solid or a liquid particle that's suspended in the atmosphere. And in terms of the different types, the different varieties, the primary pollutants, that would be dust and soot. Secondary pollutants are sulfates and nitrates. And what ends up happening is it will damage your respiratory tissue when you inhale it. And usually the way that you inhale it is just because of the wind blowing around. And there's two classifications of particulate matter. It's called PM10 and PM2.5. So if we take a picture, look at the picture on the right here, just to give you a frame of reference for sand. Fine beach sand is 90 microns in diameter. Human hair is about 50 to 70 microns in diameter. So when we're looking at PM10, that number 10, that is the size. Examples of PM10, that's dust, pollen, and mold, is about less than 10 microns in diameter. PM2.5, which you are probably now familiar with, it is less than 2.5 microns in diameter. And those examples are combustion particles, organic compounds, and metals, etc. And the reason why PM 2.5 is more dangerous for us is because normally we can filter out a lot of dust, a lot of particles just with our nose, with the mucus in our bodies, but 2.5 is so tiny that our bodies are not able to filter that out. So once we breathe that in, it like settles in our lungs. So what we could do is we could have like air filters. Right? If we have an air filter, the picture here at the top, this is an air filter that has not been replaced in a long time. So that's a thick layer of dust. If we take a picture or take a look at the picture on the right, this is the air filter from my furnace. This is a new one, the one on the left. And this one is a picture of one that I probably didn't replace for like over 6 months. So I think you're supposed to replace them every couple months or so. So you can see it does make a difference, that filters will help filter out the particles. And then the last one, the last criteria air pollutant is lead, the element Pb. It's a particulate pollutant that's added to gas, and it's used in industrial metal smelting. So during the creation of metals, and looking at the picture on the right here, you have to add lead to get that process to go. And then also back in the day in America, there used to be choices of different types of gasoline. You could get leaded gas and you could also get unleaded gas. So right now, it's leaded gas is banned. We don't have that anymore. Just like paint, we're not adding lead to paint anymore. So the reason that we're trying to create laws and things like that is because we notice that lead will bioaccumulate. It causes problems in the nervous system, and we have created legislation to stop the production of lead in gasoline, in paints. And if you wanted to take a look at this link, it's just more information about the N95 mask. We just finished talking about criteria air pollutants from EPA, but there are many other different types of air pollutants, and probably the next most popular one is volatile organic compounds, commonly known as VOCs. So these are carbon-containing chemicals. They are usually emitted by vehicle engines and industrial processes. With air pollution, you can have outdoor air pollution and you can have indoor air pollution. I would say carbon monoxide, it's both. So it's produced as a byproduct for incomplete combustion of fossil fuels, so that's outside. And then inside, if you have a gas burning stove, you can have carbon monoxide as well. So these VOCs are the most diverse group of indoor air pollutants. And I would say probably the most famous example would be that new car smell. So if you can picture that new car smell, or you can imagine that new car smell, all those good smells that you're smelling, if you like that smell, those are volatile organic compounds. So volatile, that vocab word just means that you have some type of a liquid and it evaporates into gas phase easily. So you're just breathing in the fumes, essentially. And the picture on the bottom right, this is a picture of windshield washer fluid. And I just noticed that there's a label here that says VOC content. So there are VOCs, there are volatile organic compounds everywhere. And then looking at a picture of a house, here are all the sources of various VOCs. So from the foam from your couch, that also will emit VOCs. And then this list right here talks about pesticides, formaldehyde, and in terms of like the damage that it causes, it can lead to respiratory issues and with cancer. So things can be carcinogens. So with all these air pollutants, this slide right here talks about what we can do to mitigate the problem, what we can do to reduce the amount of air pollutants that are released into the atmosphere. And this is called a catalytic converter. A catalytic converter, you're going to find it in your car somewhere between your engine and your exhaust pipe. And a catalytic converter, it's going to convert, right? Catalytic converter, it's going to convert different kinds of reactions with the use of a catalyst. And the most popular catalyst that is used in these catalytic converters is platinum. So a catalytic converter, it's an exhaust emission control device that will convert toxic chemicals into less noxious substances, less toxic substances. And it will convert actually 3 different classifications of pollutants. So the first one is the reduction of nitrogen oxide to nitrogen and oxygen. So if I have our nitrogen oxides, this NOx, with this catalytic converter, it converts this NOx, one of the criteria air pollutants, into oxygen, which we like, and nitrogen, which we like. Nitrogen's like 78% of air. The second kind of reaction that takes place in this catalytic converter is the oxidation of carbon monoxide to carbon dioxide. So carbon monoxide, that was another criteria air pollutant. You can get that to react with oxygen to make carbon dioxide. So CO, this is an air pollutant. We want to get rid of this. You do end up making carbon dioxide, but carbon dioxide is not deadly like carbon monoxide. And then the last type of reaction this catalytic converter does is the oxidation of unburned hydrocarbons into carbon dioxide and water. So within gasoline, there's octane, but there's also other hydrocarbons in this mixture of gasoline. It can convert that into carbon with the presence of oxygen into carbon dioxide and water. And so although these catalytic converters, they are effective at removing these hydrocarbons and the carbon monoxide and the nitrogen oxides, it doesn't reduce the emission of carbon dioxide, because you can even see here, like you're actually producing it as well. So in terms of greenhouse gases, it still will produce greenhouse gases, but greenhouse gases are not air pollutants where it's going to do damage to the human body. The next couple of slides are going to talk about the effects of acid pollution. Acid deposition is the deposition or the deposit of acid or acid-forming pollutants that are existing in the atmosphere and then they fall onto Earth's surface. You're probably familiar with acid rain. So acid rain is the precipitation of acid. We'll talk about this in more detail later, but there's nitric acid and sulfuric acid. With wet deposition, that's when acidic rain, acidic smog, or acidic snow ends up falling onto the ground, and then it's going to affect both animals and plants and the soil. There's something called dry deposition. So acids, they don't necessarily always have to be liquids. They actually can be in gas form and they can be in solid form. So once the wind blows, you could have these gases, these particles settle onto different structures. An example of this one would be what's pictured, all of these three pictures. So if we're looking at all these three pictures, these are examples of obelisks. So back in Egypt, these were created, these were given to Paris, to New York City, to London. And if you look at the one in New York City, that middle picture there, you'll see that the hieroglyphics are barely readable. Barely readable because the acid will end up reacting with granite. It's going to react with that stone. And if we think about why, think about in New York City with industrialization, you have more factories, you're burning more coal at the time, so you're going to have more sulfur emissions, and that sulfur is going to end up reacting with water to make the acid rain. Now with all the sources of acid deposition we talked about in the previous slide, wet deposition and dry deposition, these originate either from the burning of fossil fuels that release sulfur dioxide and nitrogen oxide, or from natural sources such as volcanoes. So you can see that these substances, they're going to react with water to either form sulfuric acid or nitric acid, which I have the reaction picture there on the right. So when we're talking about wet deposition, we're looking at these chemicals, right, that end up going into the air and then they react with water to form these acids. So that's like the acid rain. But you can also have the dry deposition where you just have these chemicals that are formed and then they just go back into the ground. So two sources. You can have wet deposition where it mixes with water, or dry deposition where it's just the substances themselves. In terms of the effects of acid deposition with the environment, we can have water pollution. Okay? So not only air pollution, but it will contribute to water pollution. And if we think about our chemistry class, we learned about the activity series of metals. So metals will react with acids depending on what type of metal it is. Once you have these metals exposed to acid rain, then these metals will turn into metal ions such as aluminum ion, zinc ion, maybe even copper ion. And these ions are soluble, as in it mixes with water. So then it's going to go into the water table. It's going to go into our bodies of water and contribute to water pollution. It can also erode stone buildings like the granite obelisk that you saw from Egypt. It can corrode cars because cars are made out of metal. It erases writing on tombstones. And then for soil, nutrients, they are leached from topsoil. So if we think about the CEC, the cation exchange capacity for the soil lab, you want to switch out those hydrogen ions for calcium and magnesium. So that's going to be an issue. And once you do that, the soil chemistry is going to change. And then you could have widespread tree mortality, like what is pictured on the right over there. Not only that, but it will affect surface water. It can kill fish, back to like water pollution. It can damage agricultural crops. So maybe not like the first thing of rain, but over time it will accumulate and maybe take a couple of years. And then if you learn plant biology, so the underside of the leaf, that's you're going to have little holes there. Those little holes, that's called stomata. Acid rain and acid deposition, it will close the stomata, preventing transpiration. So that's how plants will die. This picture here talks about the pH of precipitation in the US. So it's looking at the amount of acid rain throughout America. And if we're looking at this, just interpreting graphs, looking at the lab pH values on the bottom right-hand section right here, if you have a value or a color of orange less than 4.3, this is going to be more acidic than the color of green, which is greater than 5.3. So we can see over here on the East Coast has more acidic rain. And if we think about why, okay, we can think about population density. We could also think about on the East Coast there are more factories, there's more industry, so they're producing more sulfur dioxides, even like nitrogen dioxides to contribute to that acid rain. So after we have figured out, all right, acid deposition is destroying things, it's actually not lowering yet. New technologies, they have been developed such as scrubbers Sulfur dioxide emissions are lower, but in terms of nitrogen oxide emissions, they are still higher because nitrogen emissions, it's either going to be from factories or from the combustion of fossil fuels, which we're still doing now. And acid deposition's effects, they are worse than predicted. So we have the Clean Air Act. We'll talk more about it in a little bit. It can't restore ecosystems. So once the damage has been done, it's very hard to reverse that. So more must be done to control acid deposition. Let's talk about a concept called thermal inversion. So thermal is heat, inversion means to switch around. In general, the troposphere that we are in right now, as we increase in altitude, the temperature decreases. And also in general, warm air is lower in density, it's going to rise, causing vertical mixing. So in the city, in urban areas, with all the buildings and all the structures, the temperature in the city is a couple of degrees warmer than in rural areas. There could be a time where instead of having the warm air continuously move up and just, always have a source of warm air, there could be a situation where you have something called an inversion layer. So inversion layer, or this thermal inversion, is instead of having the cool air above warm air, you're going to have cool air being trapped underneath like a pocket of warm air. And so with this cool air getting trapped underneath the warm air, cool air is more dense, right? It's colder, molecules are closer together. Why is that a problem? It's because it's going to trap pollutants. Because normally the warm air will kind of bring the pollutants up and away, but because cold air is more dense, it's going to keep those air particles with the pollutants, with the criteria air pollutants, the VOCs, all of that within our troposphere, so we can end up breathing that in. And this situation actually happened back in 1952 in London, and it was called the killer smog. So this doesn't happen all the time, but there are times where you could have a thermal inversion. If we think about where we spend most of our lives, we spend most of our lives indoor. So there's outdoor air pollution. That is it's a very common topic, but there's also indoor air pollution. Indoor air pollution, I briefly talked about carbon monoxide and VOCs. So the amount of indoor air pollution is about 25 to 60% greater than outdoor air pollution. And in terms of examples, you can have tiny living organisms such as dust mites. You could have mold, bacteria, carbon monoxide, radon, which is a radioactive gas, allergens, asbestos, which I'll talk about in the picture on the top right, tobacco smoke, formaldehyde, and other VOCs. And even animal dander, that can be considered as an indoor air pollutant. It will worsen asthma symptoms. So asbestos, picture on the top right here, this pink fluffy stuff, this is insulation. Insulation, what you would put either in the walls of your home or in the attic of your house, is to help you conserve energy when we were talking about weatherization. And a long time ago, this insulation was made out of asbestos. And if you were to zoom in, this is what it looks like zoomed in. So it almost looks like little tiny shards of glass. So if you're going to breathe that in, it's going to cut up your tissues, right? Cut up the tissue in your lungs. So now insulation is not made out of asbestos after we have figured out, oh, it does do damage to our health. So with all these air pollutants, it can lead to something called sick building syndrome. Sick building syndrome. It's a sickness that's produced by indoor pollution with general and non-specific symptoms. So it's solved by using low toxicity building materials. So instead of asbestos with insulation, we use something else. And also with good ventilation, because we have good ventilation, if we have good airflow, then all those pollutants are not like trapped within the building that you're staying in, kind of like the thermal inversion type of thing. And in terms of symptoms with this sick building syndrome, can include headaches, breathing difficulties, allergies to asthma, cancer, emphysema, and various nerve disorders. And if you're taking a look at a picture on the right here, it says, warning, entering this area can expose you to chemicals known to the state of California to cause cancer and birth defects or other reproductive harm, including carbon black and mercury from copy toners and fluorescent lighting. So if you work in an office building, you have copy toner, or even if at your house, if you have copy toner, right? Breathing in those particles is a form of indoor air pollution. And then with the fluorescent lighting has mercury in it. And so that is why it is an indoor air pollutant. This slide is talking about remediation and reduction strategies, different ways that we can improve air quality or we can reduce the amount of air pollutants that enter the atmosphere. And if you're looking at this list, a lot of them are money related, where it's providing incentives, right? So discounts, things like that. And then for something like number 5, distributing solar cook stoves to developing countries to replace coal and firewood, because combustion of coal and firewood leads to air pollutants. So I'll let you take a look at this list. It's also in your Barron's book. When we're thinking about all of this air pollution, how do we fix it? Most commonly, the best answer that you would write on an FRQ is to create legislation. So this Clean Air Act of 1963, which was amended in 1967, 1977, and 1990, it was made to control air pollution on a national level. It required the EPA to develop and enforce these regulations to protect the general public from exposure to airborne contaminants that are known to be hazardous to humans. So in terms of like factories, right, there's regulations, like you can no longer produce X amount of SO2 or X amount of NO2. It's going to be regulated, and it required comprehensive federal and state regulations for both stationary, so industrial like factories, and mobile sources of air pollution. So mobile thinking non-point source like automobiles. And it addressed acid rain, ozone depletion, and toxic air pollution. It established new automobile gasoline reformation requirements, and it was also the first major environmental law in the US to include a provision for citizen suits. And in terms of did it work, take a look at the picture on the right. So this is the LA skyline on the left. On the left, this is the LA skyline in October during the 1970s. So in 1970s, LA was like known for a lot of photochemical smog. But if you take a look at the right, in the late 1990s, the air quality has improved. So this Clean Air Act, it has worked, right? It is successful. The Clean Air Act is something that has been done in America. But the Montreal Protocol in 1987, this is on a global scale. This is a success story. So the Montreal Protocol, 180 nations agreed to cut CFCs. CFCs stands for chlorofluorocarbons. Typically we don't say it, we just say CFCs. You can find CFCs, or you used to be able to find CFCs, in coolants and aerosols. So coolant, like the refrigerant in your refrigerator, so what's keeping your refrigerator cool. If you drive a car on a hot summer day, that AC that you turn on, that is a coolant. It used to be made out of CFCs, but now it is no longer made out of that. It used to be called Freon. And then aerosols. So aerosols used to have CFCs as a propellant. So when you try to press the button, like for hairspray, when you're pressing down on that to get that hairspray to go, it used to be made out of CFCs. And so the agreement initially was to cut the production in half. So why do we even want to cut the production? If you take a look at the picture on the top right-hand corner, this is a picture or an image of the ozone layer in the stratosphere. So we learned that tropospheric ozone, not good for us to breathe in, but when it's in the stratosphere, ozone, there's a layer of ozone, it's called the ozone layer. It's a great thing because it protects us from UV radiation from the sun. So back in 1971, looking at this image here, compared to the image in 2000, you could see that by cutting the amount of CFCs that enter the stratosphere, it has made an effect, right? So here you can see like the red is when you have less ozone. And then over here in 2000, you have less red or more green, so you have more ozone. And just following up with here, initially they were cutting production in half, and then follow-up agreements deepened the cuts, and advanced timetables, and addressed other ozone depleting chemicals, so not just CFCs. And then today, the production and use of ozone depleting chemicals has decreased by 95%. And the ozone layer is beginning to recover. So you could see in the stratosphere, the picture on the top right, it has been healing. And this is like a success story where if a whole bunch of countries get together and decide, okay, we're going to slowly phase out CFCs. We're going to replace it with something new. Something new. For my car, I use R134A. I can't remember exactly what the chemical is. I saved the bottle, but that's at school right now. But there has been replacement, and it's still a coolant. So it will still keep the car cold in the summer. And And then challenges still face us. So CFCs, they don't decompose very readily, so they're still going to remain in the stratosphere for a long time. And then some nations, they can ask for exemptions to the ban and then they can still use CFCs. So we haven't cut it out completely, but you could see, just by looking at this graph, this projected, this extrapolated data here, if there was no protocol, if countries did not band together, then we would probably have even more and more and more and more depletion of the ozone layer. But with the Montreal Protocol, it's heading in the right direction. All in all, the Montreal Protocol is a success. It's considered the biggest environmental success story. Policymakers included industry in helping solve the problem, so it was a collaborative effort. Implementation of the plan allowed an adaptive management strategy that changed strategies in response to new scientific data, technological advances, and economic figures. So it was always looked at over and over again to see if they needed to improve or modify anything. And this Montreal Protocol, it can serve as a model for international environmental cooperation. So a whole bunch of countries get together, they believe in this, they're taking methods to slowly do something. It can work. Here's a list of a few other laws. The ones that are in italics are ones you do not need to know for the APES exam. You do need to know about the Kyoto Protocol in 1977 and modified in 2001. And it was an agreement between 150 nations requiring greenhouse gas reductions. Right now, you might not be familiar with the Kyoto Protocol because we have transitioned more to the Paris Climate Agreement. But Paris Climate Agreement, I believe, is not on the APES test. So there's a lot to know besides Montreal Protocol and Clean Air Act is the Kyoto Protocol. In conclusion, indoor air pollution is a potentially serious health threat, but we can significantly minimize these risks. Outdoor air pollution has been addressed by government legislation and regulation in developed countries, and reduction in outdoor air pollution represents one of the greatest strides in environmental protection. There's always room for improvement, especially in developing countries, but hopefully we will get there one day. If you wanted to stick around, we could do some practice questions. So practice question number 1, the Clean Air Act does all the following except: A, allows higher levels of emissions of some criteria pollutants. B, provides funds for pollution control research. C, allows citizens to sue violators. Or D, sets standards for air quality control. Which one do you think it is? The answer is A, allows higher levels of emissions of some criteria pollutants. We want to lower the levels. We don't want to increase the levels. Practice question number 2. Which criteria pollutant is colorless, odorless, and poses a risk to humans even in the smallest amount? Is it A, sulfur dioxide, B, nitrogen dioxide, C, tropospheric ozone, or D, carbon monoxide? It is carbon monoxide, colorless, odorless, and poses a risk to humans even in the smallest amounts. This is one of the 6 criteria air pollutants provided by the EPA. Practice question number 3. The Montreal Protocol addressed A, global warming and was not successful, B, criteria pollutants and was successful, C, ozone depletion and was successful, or D, acid deposition and was successful. Correct answer is C, ozone depletion. So when you're thinking Montreal Protocol, you're thinking CFCs. They're trying to get rid of CFCs because it will deplete the ozone layer, and which layer is that? That's in the stratosphere. All right, so we want to eliminate CFCs because it will interact with the ozone that's in the stratosphere. And we want to keep the ozone in the stratosphere because it protects us from UV radiation. Practice question number 4. This is the last one. Short answer. What is a catalytic converter and what are the 3 main pollutants does it convert? So a catalytic converter, that's that machinery or equipment that's in your car, somewhere between the engine and the exhaust pipe that will convert the 3 main pollutants into something less toxic. So the first one was to convert the NOx's, right? So that one went into nitrogen and oxygen, which we liked because both of them are in our atmosphere already. The second one was to convert carbon monoxide. So carbon monoxide in the presence of oxygen to make that turn into carbon dioxide. And then the third one was any unburned hydrocarbons. I'm just going to put an X and then Y. So if I do any unburned hydrocarbons, mix that with oxygen, I can make carbon dioxide and water. So all of these right here, these are not the criteria air pollutants. Just one last word on air pollutants. Common ways that you're going to hear these air pollutants is you're going to hear it as NOx, SOx, and VOx. All right, so NOx, SOx, and VOx, just wanted to throw that out there. And that is it. Thank you for listening.